Okay, what we're going to do here is try to clarify some things that we did in class with the piecewise parametric number 4. So what I did here is I took autograph and I drew in these 3 segments. That's what we had previous. And I want the circle that circumscribes this triangle that goes through all 3 points. So what I can do here is I can highlight these 2 points. And then if I right click, then there should be, here's a midpoint, but I also want a perpendicular bisector. So here's my perpendicular bisector, so I can click on that. That would draw this line right here, this one. And so that would give me a perpendicular bisector. I get another perpendicular bisector here, and then I go ahead and solve for y equal to x. So if I click these 2, solve, I said that wrong, f equals to g. And so if I solve that, that gives me my point here in the middle. And so when I click on this, my point turns out to be negative 1.1 and 0.1. With that point, then I can use this point and find the distance between that point to any one of these other points that are on the triangle. And when I do that, that will tell me my radius. And so my radius should be just a little bit over 3. I think we found it to be 3.1, but a more accurate way is to go to the square root of 9.62. And so that gives me my distance, which is my radius. So when I write this in parametric form in autograph, all I do is I write my x and I go comma on my y. That would give me my circle. So that's the picture I have right now. Okay, so now the problem is to draw the same triangle but replace the bottom edge with an arc of a circle where the full circle would pass through each vertex. And so with this, I'm going to start here and go to this point and then go along the arc and then back to my starting point. And so I don't need these other 2 pieces, but I have those here right now. And so how we did this before is we called this 2 seconds and this 2 seconds. My original thought was to call this arc 2 seconds as well, but it's just easier if you go ahead and take this circle and with this find this angle measurement, call it theta, and with that angle measurement, since it's in radian, the radians will measure this out perfectly if we use that angle measurement. And so when we set up our table, we have our t, x, and y. We're going to start at time 0, 2, and then at time 0, I'm going to be at 0, 3, and at time 2, so I go to here, I'm going to be at 2, 0, and now I don't know what this time is, this next one. But I do know it's going to be something where I end up at negative 4 and negative 1, and so at some time. How I'm going to figure out this difference is just find this angle measurement, and it turns out that it works. I might have to do a little translation in there as well, but it should work. So to do that, I need some background information. If you ever have a slope, the slope is the same thing as the tangent. So if I take the slope with respect to a vertical line, call this theta, this would be my delta y, this would be my delta x. And with that, delta y divided by delta x is the same thing as the slope as it is for the tangent of theta. And that's what's going to help me find ultimately this central angle. And so if I draw straight across here, the horizontal, I need to find this angle right here and this angle right here. If I can do that, then I'm in business. And how I do that is I find the slope of this line and use that tangent, and find the slope of this line and do the tangent as well. So I'm using this center of the circle, this point, and then this point. This point is 2, 0. This one is negative 4, negative 1. And this point would be negative 1.1, comma, 0.1. That would be our center of our circle. Okay, so what I'm going to do is I'm going to find the slope of this line right here. So I have 2 points, negative 1.1, comma, 0.1, and then the other point would be 2, 0. So if I find the slope, I'm going to go y minus y, which would be 0.1, and then negative 1.1 minus that would be negative 3.1. That would be the tangent of my theta with respect to the horizontal. And so if I solve this for by taking the inverse tangent of that thing, I get negative 0.0332. So that little itty bitty angle measurement in there is 0.0332. Oh, I'm sorry, it's 0.0322. Okay, now similarly you can do the same thing with the center and this point here to find the slope of this line, and then I can find that angle measurement there. So I just went ahead and calculated this one the same way, and so if I look at this going straight across is pi, then I got to subtract out this magnitude, so I just take out the 0.0322, and then I need to subtract out this one too, which is subtracting out the 0.3625, and I get approximately 2.747. So if I use 2.747, that would be the time that I could take to go across here, because this theta is represented as a part to whole, and if I use just my normal cosine and sine curves, this right here, and I put in 2 pi, I'm going to go all the way around. But since I'm only going part of it, if I find this angle measurement, which corresponds with how far I go, that's going to give me a 2.747. Okay? So when I write my equation, I have to do a translation and adjustment of this, but it shouldn't be too bad. Now notice that I already started at time 2. And then when I started at time 2, then I also had to translate it by 0.0322. So when I do this, I'm going to have to do x is equal to square root of 9.62 cosine of t minus 2. Now the question is, do I add 0.0322 there or subtract it? And I think to get it advanced a little bit, I'm going to have to add it. So it's 0.0322. That pushes it forward to the right. And then I still need my minus 1.1. And then my y value is going to be square root of 9.62 sine of t minus 2 plus 0.0322, and then plus 0.1. The only problem here, though, is that this would travel in a counterclockwise direction. I want to travel in a clockwise direction, so I'm going to change my y coordinates. That takes my y coordinates from going up like this to going down like this for the same exact x coordinate. I'm going to punch this into my calculator and I'll show you the result. Okay, now I've got this value of 2.747. That has to be the difference between these two values. So when I'm doing my intervals, I need to use not just 0, 2, 4, and so on. I need to use these intervals. I still want this last segment to take 2 seconds, so I'm still going to have a difference there of 2. And that's going to bring me back to 0, 3. So when you set up your parametric equations in your piecewise situation, you're going to have to take these different intervals into account. So when you type this into your calculator, that's what you're going to have. So I did put this into my calculator. And if I look at the y equals, this is the equation of this, oh, that's the x coordinates though, of this first line, t less than 2. Because I started at 0, and then my change is 1 unit per unit of time. So it's the change here divided by the change here. Then I have the cosine portion of this for the x, and just double check your parentheses and stuff. And I start that at 2, and then I run that up to 4.747. That's going to give me the x coordinates on this right here. And then to finally end it up, I have this last equation. Remember, you have to translate every equation. I start at 4.747, so if I just write the equation of this line, I translate it over. And so then I have t greater than or equal to 4.747 and less than 6.747. That's my x. Then if I scroll down here to my y's are done very similarly. You just got to make sure you keep this in order. This took me a long time, which will take you a long time too. And so if I do this one, this would be my y coordinates. So this is my change in y here. I start at 3, and then I go down by 3 over an interval of 2. So that's negative 1.5 per unit of time. And so t is less than 2. And then here's my negative. I'm using negative sign because I'm moving this way. And then this would be minus 2. And then plus this little bit. If you don't understand that quite fully, I can explain that in a second. But then we still have these intervals, and most of the things are still the same. And remember this translation here. The last thing is, yes, I put this into my equation here because if you start a regular cosine graph right here, it's going to start straight across. So if I did not do this extra 0.0322, I would be starting right at this point on my graph rather than this one here. So I nudged it ahead by 0.0322. Since I'm going clockwise, I nudged it ahead to start here. That's where I got this value from. Or that's why I put it in there, I should say. And if I plug in time 2, this becomes 0, which is what we want for the cosine and sine to start at this rightmost endpoint, but then we nudge it ahead to start here. That's what that reason is. All right, I hope this helps. And take care, figure out some more of your graphs. And I'm finding a lot of enjoyment in this. I hope you're finding some too. Thanks.